Hey, Applied Precal, welcome back. We are continuing on with our equations of lines. I apologize for all the practice that I gave you for the first part of it, which was slope-intercept form. Uh, but I need you to trust me that the practice really helps out, especially with these topics. We're moving on to our second type of equation. This is going to be called slope-point form. Now, if you remember, slope-intercept form was an equation of a line that told us both the slope and where our y-intercept was going to be. So by going by the name, slope-point form, it's going to tell us our slope, and it's going to identify a point on the line for us. The equation itself can be written in one of two ways. I'm sure you could have a different way as well, but usually we have it in one of two ways. It's going to be y minus y1 is equal to m times, open your brackets, x minus x1, close your brackets. The other way that you can write it is if you're used to writing it using our slope formula, y2 minus y1, etc. We could do y2 minus y1 equals m times x2 minus x1. Now, why does this equation work? Well, I'm going to show you the Precal side of things. I want to show you how we come to this equation just using some of the formulas we already know. And then we'll get into some practice, and I'll give you some practice for this type of equation as well. Okay, then again, what I'm going to show you is essentially the Precal side of things. We need to know where our equations come from and why they work the way they work. You don't need to memorize this. Again, I'm just trying to show you that I'm not just throwing an equation at you. There's a reason why we use one of these two for slope-point form. So you need to remember in slope-intercept form, it's y equals mx plus b. We're going to use that equation again. We also have to remember a little bit further back, the equation for slope, m is equal to y2 minus y1 over x2 minus x1. Now, we write our equations like that. Don't forget, when you're dealing with a slope, we have these brackets in there. It violates BEDMAS otherwise, but we use it so often that we don't usually throw the brackets in there, but you do have to include them when you're doing the calculation. To find our derivation, we're going to use some information. I'm going to make some numbers up. So I want you to consider a line that has a slope of 3 and passes through the point 1, 2. Well, there's a few things that we can figure out from this information. We could essentially figure out the equation of a line using slope-intercept form. That's what I made you do last week. We're gonna put the numbers slightly differently in this case here. Okay, so I'm using one of my equations. I'm going to be using the slope equation. M is equal to y2 minus y1 over x2 minus x1. I know what the slope is. That's given to me as 3. So I replaced m with 3. I also know what one of my x values is and one of my y values are, based on that one point that's given to us. Doesn't matter if you choose x2 or x1 or y2 and y1. Typically the first one we see is usually the number 2, so I've just plugged those into my equation. I've left x1 and y1 as variables because I don't know what they are. Now I can rearrange this equation. For instance, if I want to get this 1 minus x1 out of my denominator, out of the bottom of my fraction, I can multiply both sides by 1 minus x1, and then it will end up next to my 3. I'm going to do that and show you what it looks like. Okay, so cleaning everything up a little bit, we end up with 3 times 1 minus x1, should be x1. My mistake there. 3 times 1 minus x1 is equal to 2 minus y1. We can also flip those two positions around, so the 2 minus y1 can come first, and the 3 times the x variables come second. Looks like that. And the reason why I've written it this way is, if you remember, our equation is y2 minus y1. Well, this was my y2 value, so y2 minus y1 is equal to slope times x2 minus x1. That's where our equation comes from.